Hello all, welcome back to lecture 17 today. We shall continue on 3-5 gallium arsenide MESFETs from the last lecture. So, we still have around 4 more lectures on gallium arsenide, but I would like to emphasize on the fact again that many of the concepts in terms of device layout, geometry, microwave performance, etc., are more or less identical for all kinds of FET, especially 3-5 MESFETs, HEMTs, gallium nitride HEMTs. Okay. So, many of the things that we discuss here will be pertinent in case of HEMT also later on. Okay. So, with that we will come to the whiteboard here. So, in the last lecture we basically ended at different kind of grading profiles for engineering the transconductance profile, and what kind of transconductance profile gives you better linearity. It is a flat kind of a GM. If your GM stays flat, that means it is a linear gain, and that helps you in achieving linearity at the system level. And to get a flat GM, people have found that you can change the doping level in the MESFET, especially if your doping is higher towards the far away from the gate, then that helps actually. Okay. So, that is all fine with the physics, we talked about saturation, the drain pinch off, and the IV relation, etc., etc. So, today we will come to more practical aspects of different types of MESFET structures and how they are fabricated. So, in this you can see there are 4 different actually images or schematics of MESFET, and basically it shows the evolution of different generation of MESFETs right from 1960s 70s till you can say today. You have to remember that in 1970s onward, gallium arsenide MESFETs emerged as the workhorse for microwave, analog microwave electronics. So, and as the device evolved, the performance at the system and the subsystem level also had evolved over the many decades. So, the first generation, you can see this is the first generation where you have a semi insulating gallium arsenide substrate. When you say semi insulating, people add chromium, okay, to compensate for the background impurity and to make it kind of insulating. And then on top of that you do ion implantation of n type, silicon would be an n type dopant. So, if you implant on top of that, you get this active layer which is n type dope, and you make a source and drain contact. Here there are many problems, for instance the chromium can out diffuse to this active layer. I mean the chromium would be there in the active layer, okay, and so it will kill your mobility, it will reduce your mobility, it will reduce the device performance. Not very good to have the active channel also overlapping with the the chromium dope insulating substrate. Another problem is that your source and drain contact resistance will be very high, because this n type doping is not is moderate, it is in the range of 10 to the power 17, and so the contact resistance is pretty bad, because for contact resistance you need very highly doped region, but if you cannot, if you dope it very high, then the channel it will not pinch off, and the gate will for instance leak. So, this was the first generation only. The next generation was the first idea to implement was that you introduce an extra layer here which is called a buffer layer to prevent chromium from out diffusing and reaching the active layer. So, and in a way you are not allowing the chromium to come to the active layer, so your mobility improves, okay, your mobility improves. And this buffer layer people use it as an undoped layer. You can do epitaxial growth, for instance people do MBE or MOCVD, and in that case we call it epitaxial gallium arsenide wafer or epistack. In MBE and MOCVD you can grow atomic layer by atomic layer, so you have different layers you can engineer and grow. The other method is ion implantation, where you have this high energy ions that you bombard, say silicon for n type doping, you bombard and you convert it into n type, okay, as the case may be. So, ion implantation is the other approach. MBE, MOCVD epitaxial layers will generally give you better performance. However, advances in ion implantation techniques have enabled over the last many decades that gallium arsenide MESFETs using ion implanted layers also can give very good outstanding performance, and in many cases commercial foundries will also use ion implanted gallium arsenide wafers to a large scale, because the cost is much less for non epitaxial ion implanted wafer. Okay, so, this was generation 2. In the third generation what people did is that they put a highly doped layer below the source. This is your source and this is your drain. So, before this below the source and the drain they put a highly doped layer, so that your contact resistance becomes lower. Anytime your metal touches your semiconductor you have a contact resistance, and the idea is to minimize this contact resistance, it is a parasitic resistance. So, by putting a highly doped layer you can actually reduce the contact resistance. Now, this can be ion implanted, this can be also epitaxially grown. However, the drain or the gate must not be sitting on top of n plus layer, otherwise the gate will start leaking, because the n plus layer is very highly doped. So, what happens is that if you have a layer like that n plus, you etch it away you physically remove the layer by something like say reactive ion etching or plasma etching. You remove the layer away so that you expose the nominally doped channel layer. This is your channel layer which is moderately doped, say in the range of 10 to the power 17 per centimeter cube, and you put the gate there to form a Schottky contact, correct. You form a Schottky contact there, and you still have the buffer layer of course to prevent chromium out diffusion. And in the 4th generation, which is more latest generation in a way, you can say, when I say latest, it is still a few decades old, you have the N plus contact to reduce your contact resistance, but you also have this feature gate. You see the gate is further etched down, the channel is further, this entire is channel actually, this is your entire is your channel. However, you have etched the channel partially to some extent and then put down the gate. This is called gate recess. Okay, this is called gate recess because you have recess etched the channel and put down the gate. So, your effective channel thickness below the gate has reduced. This is necessary for scaling. Okay. When you scale the device dimension, your source drain spacing LSD reduces, and you have to reduce that to scale the device down for higher speed, for instance, okay, for better noise, for instance. So, when you do that, then your, as I keep mentioning, as I have told you before, if your gate length Lg has reduced, then your gate to channel, the channel thickness say H also has to reduce. The ratio of Lg by 10 has to be at least Lg by H has to be at least 10. So, your recess helps in having thinner channel. So, that gives you a better gate control. Okay, it gives you better gate control, which means your GM, your transconductance GM improves, and GM improving is extremely important for improving the gain as well as improving the noise performance, as we shall see. Alright, and also this recess helps improve the breakdown VBR, we will see how, but recess also helps improve the breakdown by tailoring the electric field profile. So, you have electric field that goes like that. So, you can tailor or you can engineer electric field profile by having a suitable gate recess, and that helps in the breakdown. So, these are the different generations in how in which gallium arsenide MESFET structures have evolved over the decades. Okay. So, hope this is clear till now. Now, for instance, to fabricate the actual transistor, there are two approaches. One is a gate self aligned process, and then there could be a non self aligned process where you do not need to self align the gate. Okay. But again, there is an ohmic priority, there is a gate priority process. I will come to both of them subsequently. Now, again, these images are taken from different books. So, this image is taken from this excellent book called Microwave Field Effect Transistor, for instance. Okay. So, now in gate self aligned process, what happens is that first you deposit the gate metal, you define the gate, and around that gate you deposit the source and drain in a self aligned way, which means you do not have to worry about the misalignment between the source and the drain, because your process ensures that your source and drain are aligned to the gate naturally. So, what do I mean? So, you can see this structure, this is number 1. So, this is the same structure, the same flow, by the way. The first step is that you have this gate metal, you see this white layer, it is a gate metal. Okay. This dot dashed line is the N channel, the actual channel layer where doping is there. So, this is a gate metal, and then you have a photoresist. Actually, the photoresist is coated everywhere, but then you can expose it, hard bake, and then develop it so that you can have the photoresist only on this part, and rest everywhere the photoresist is dissolved away. This is a standard lithographic practice. If you are not very sure of these things, you are encouraged to take a course on basics of fabrication or lithography. There are many such excellent courses even from IISc, and you will understand what lithography means. So, you basically it is like a photographic exposure. So, you have this photoresist, which is an organic polymer which is protecting the gate metal only in this region, the rest of the region is not protected. Now, you subject this to, for instance, a high power plasma of a suitable flow rate, suitable RF power, ICP power, and that plasma will basically etch the metal away. In some cases you can even do wet etching. Wet etching is you using a chemical to etch the like a liquid solvent, some kind of etchant to remove the metal away. In plasma etching it is a dry etching, say chlorine or argon based some kind of recipes that will etch the metal away from everywhere except below the gate. So, except below the photoresist. So, except below the photoresist the gate metal is here, but everywhere else the gate metal is removed. However, you can use a combination of dry and wet etch to make sure that there is an undercut. You see this point, that is the undercut, which means the etchant has etched the gate metal below the photoresist also to some extent. That kind of is usually achieved by a wet etching process, for instance when you have an isotropic etch more or less. So, you are able to etch the metal below the photoresist also to some extent. Okay. Now, what happens is that now on this structure you deposit a source drain metal, the metal that you are going to use for ohmic contact or source drain, you deposit everywhere on this. Okay. So, that is what they have done in this number 3. Okay. They have deposited the ohmic metal everywhere. Okay. It is everywhere. Now, you dip the entire wafer in a lift off solution. This process is called lift off, okay, or float off. What does lift off means? Now, when you dip this entire wafer along with the structures and everything in a suitable chemical agent, or a liquid, which is called a lift off liquid. It could be acetone, for instance, okay, depending on the photoresist that you are using and the process that you are using. Wherever there is photoresist, in this case this is a photoresist part, this is your photoresist part PR, okay, that part will be washed away or dissolved away, and whatever is on top of that will be also removed. It is called lift off process. So, whatever is on top of, there is a photoresist layer, and whatever is metal is on top of photoresist will be, the liquid will come and the entire thing will be washed away. So, if entire thing is washed away, you are left with this kind of a structure where there is a gate, right, and there is this gap here, this gap, which is the gate drain spacing and which is the gate to source spacing. These are defined by the undercut here, these are defined by the undercut. So, it is a self aligned process. We are not worried about aligning the source and drain with respect to the gate. When I say aligning, in lithography, when typically you have different layers of metal, you need to align one metal layer with respect to another layer, otherwise there will the the spacing between two different metal layer will be off. Suppose you have a gate here and you want the drain to be, for instance, 1 micron away, then you have to align the second layer of drain with respect to the first layer of gate, so that your alignment gives you a 1 micron spacing between the two metal pads in the lithography. In that case, you are able to fabricate this device. However, in a self aligned process, you are not bothered so much, because the undercut will define how much spacing you have. Of course, the undercut cannot give you arbitrarily large spacing. So, this is a very self aligned. Processes usually give very close spacing between the gate and the drain, which means your breakdown voltages will be low, but you can have excellent cutoff frequencies and therefore excellent noise performance, for instance. Okay. So, this is your self aligned process, and this lift off that I talked about is actually only used in 3-5 or compound semiconductor fabs and foundries. This process is not used in CMOS fabs, okay, more or less. Okay. So, this clear till this point of time. Now, there is a gate priority self align, and then there is a ohmic priority self align. What it means? A gate priority self align means that the gate stack will come first, just like I have discussed here. Okay, I have discussed this process. This was just a general schematic, but this also is a representation of the gate first process or gate priority process, which means the gate metal will come, which is this, and then this is the gate metal actually, and then you are protecting the layer, etc., etc. The source drain metal comes later on. The key here is that whenever you form a source drain metal, typically you have to do a high temperature anneal of the source drain metal, high temperature anneal of the source drain metal, so that the contact becomes better. Okay. So, here it is a channel layer here, but you usually have an N plus layer also, but whenever you do a high temperature anneal of the source drain contact, by high temperature it can be 600 degree, 700 degree, for gallium nitride it could be even 800 or 900 degree in field effect transistor. So, you do a high temperature anneal, so that the metal kind of helps improve the contact resistance. The metal could diffuse, metal could spike down, and it will make a better contact with the layer below. So, that high temperature anneal will tend to damage the gate, okay, if your gate is not done in a particular way. What I mean is that when you do a high temperature anneal, there is all kinds of probability that your gate leakage will start happening, because the gate will start leaking. You want the gate to be a very good Schottky contact, and high temperature anneal is usually not good for Schottky contact, because the gate might start leaking. Okay. If the gate forms a better contact, which when I say better contact, it tries to become ohmic, then it will start leaking a lot. So, high temperature anneal is not good for gate. However, in gate priority process or a gate first process, what they do is that you need to choose the gate metal very wisely. So, the gate metal has to be such that it can withstand very high temperature. When I say very high, 600 to 800 degrees Celsius more or less. So, people use this category of material called refractory metals. Refractory, they can actually go to high temperature, say tungsten. Instead of tungsten, people typically use say titanium tungsten combination or titanium tungsten silicide, okay, with silicon, or a tantalum silicide. There are other choices also that are being used, but this kind of material, tantalum silicide or tungsten, etc., are metal stacks that can go to sufficiently high temperature and are called usually the refractory metals. So, if you use that as a gate metal, then you can do a high temperature source and drain anneal later on without compromising on the gate contact or the gate process, because your gate metal can withstand high temperature. So, what it shows in this image is that exactly what I had shown in the previous slide here. However, you have a gate metal here, you have a masking material, you can do a photoresist or a masking metal and then you etch away the metal everywhere. Okay. This part is your ion implanted channel, for instance. Okay. Then you can do an ion implantation around this as a mask. You can use this as a mask and you do ion implantation so as to form a highly n-type dope contact. This is an ion implanted process. This is not an epitaxial wafer, as you can see from the figure, but it holds true for even epitaxial wafer also, this process of gate priority or gate self align first process. So, after that you again do a, you can do a passivation. This passivation is very critical for actually passivating or protecting the surface and protecting the traps on the surface, so that you can get minimal current collapse, and that is something we will talk about subsequently when we discuss HEMTs and other devices. But current collapse is a terrible phenomena that is a problem in most of 3-5 or compound semiconductor transistors, and so silicon nitride passivation is a more or less a universally used passivation layer. So, you have to give a passivation there, then you have to remove the passivation below the point where you are going to put the drain metal. You do not want the drain metal to sit on the silicon nitride, because that is terrible. It will not allow the drain metal to form a good contact to the layer below. So, you have to etch away the silicon nitride below the drain, below the source, and then you form the ohmic contact, ohmic source, and then you anneal so that the N plus region below the source and drain can have a very good contact resistance with the metal there. When I say very good resistance, it means a very low contact resistance there. Okay. In this case, the high temperature anneal of the ohmic process will not affect the gate, because you are using a gate refractory metal. Okay. And you know, you can use the gate metal as the mask actually in some way for self aligned process. Another advantage of this kind of a refractory high temperature resistant gate metal is that your gate reliability improves. When I say gate reliability improves, oftentimes, not oftentimes, for any practical or commercial application you have to qualify your device, and for that you need to check and evaluate the reliability of your transistor. There are many ways in which reliabilities are measured. There are many stresses that you have to give: electrical stress, thermal stress, etc. So, when you give thermal stress, you go to high temperature and you do an accelerated lifetime testing. In that case, if you use a refractory metal, the metal diffusion would be lower at higher temperature, for instance, for this kind of refractory metal. So, you know, the metal will not have a tendency to diffuse into the layers below. Otherwise, if you use just a you know, the titanium layer or some kind of layer as a gate, then that metal will basically try to diffuse to the layer, you know, the gallium arsenide layer below at high temperature stress, which you do for qualifying the reliability of the transistor. And if your gate metal starts diffusing below, then that is a reliability problem, because it leads to early breakdown or early degradation of the device. There is something called mean time to failure or mean time to breakdown that reduces at high temperature. So, for better reliability, this kind of refractory metals are good to use. However, you know, self aligned processes do not give you very high gate drain spacing, and so your gate drain breakdown could be low, and it's also you need a refractory metal here. So, those are other complications in terms of the gate priority or gate first, you know, align process. So, that brings us to the ohmic priority process, where the ohmic contact is, and this is again self aligned, however, but ohmic priority process is such that your ohmic metals come first and the gate metal comes later, which means your gate metal will not have to withstand high temperature, because after you do the ohmic metal, you are going to do a high temperature anneal to form a good ohmic contact, and thereafter you will do passivation or whatever, and then you will put the gate. So, the gate will never see the high temperature anneal. So, you can see a process flow here again from this excellent book called Microwave Field Effect Transistors. You know, you have this is again an example of an implanted wafer, because this is a little older book. So, at that time ion implantation was the typical process, but you can extend this process to epitaxial wafers also. So, you have an implanted layer which is your N type, you know, this is semi insulating substrate, this dashed line is your N layer, you know, the channel layer, and then you have photoresist that you are spin coating, and then you are going to, this is not SiO2, this is actually your resist. Okay? There people are using 3 types of resist here, you see, because of the way you shape the gate. You want a different shape of a gate, you have to use more than one layer of photoresist, maybe bilayer, which is 2 layer, maybe tri-layer, which is 3 layers. You might have to use 3 layers of photoresist to actually get the profile that you want, or the gate metal profile you want. So, in this case you use a multi-layer resist, which means photoresist level 1, 2, 3, you know, you are using different types of photoresist. Then you selectively open some area, you do not selectively open some area. You use the one photoresist as the mask over another photoresist. You see this photoresist profile, this has a photoresist profile of like that, sorry, something like that. Okay. So, there is an undercut, this is a photoresist 1 for instance, this is photoresist 2. So, different photoresists could be sensitive to different extent when you expose them to UV light. All these processes need UV exposure or UV light to actually develop for the lithography. So, different photoresists have different sensitivities, so they can expose and they can develop different extent, and you can get this kind of a photoresist profile. After that you bombard with silicon ion or you can, or rather I would say you implant silicon, so that you form an N plus layer here, N plus layer there for source and drain contact. Okay. And then you make a silicon dioxide passivation around everything. Remember, there is no gate metal till this point. Okay. No gate metal has come, this is not a gate metal, this is just a photoresist layer. You can sputter silicon dioxide. Okay. It's a sputter is another technique where you have a target, you bombard with ions and you can sputter this material onto a substrate or a wafer that is sitting very close by. So, you sputter silicon dioxide, you get a profile like that, and then you again removed and then you remove the photoresist. So, you see this point has no photoresist now because you have removed the photoresist. The only objective of the photoresist was to shape the profile around that point, and you have done that. Now, you will remove the silicon dioxide selectively across the area where you are going to put the source and drain. So, there is no silicon dioxide here, there is no silicon dioxide here. Okay. Now, you are going to put the metal there, you are going to put the source and drain metal here, this is silicon dioxide. Okay. After you put the source and drain metal, you do a high temperature anneal, we call it rapid thermal annealing, RTA. Okay. This is the ohmic annealing, always there is an annealing to improve the contact resistance, and after that you put a gate. You see, you do a photolithography process, you define the pattern, you open the photolithography process in this region, so that whatever metal you deposit will take the shape of this. So, eventually your gate looks like that, metal, this is your gate metal. Okay. And it need not be silicide or tungsten or some kind of a refractory metal, it could be titanium gold for instance. And then you have the passivation, silicon dioxide around it, silicon dioxide around it. Okay. And then you have the metal drain, you have the metal source, and below the source and drain you have N plus N plus. Okay. And this is your channel anyways. Okay. So, this is a self-aligned process, but it is a ohmic priority self-aligned process. Okay. The advantages of this also, of course, you know, you do not have to use a refractory metal for instance, but you need to use more photoresists to define the profile. Okay. Now, that is fine, but there is also in most MESFETs people use a recessed gate, as I talked in the first slide of this presentation, and recessed channel is a necessity because it helps you improve the breakdown, it also helps you have better control of the channel, therefore you are going to get better transconductance or GM. How do you do channel recess? There are many ways of doing channel recess, but one of the ways in which channel recess is done, for instance, after you form the ohmic metal, you do a photoresist spin coating, but you develop it or selectively pattern it on this part. So, you have only this part that is open, and then you etch. When you etch, you can use a combination of dry and wet etch, or you can use more tailored etch in either way, so that you have an undercut like that. You know, you can get an undercut below the photoresist also a little bit, but this part is etched away, a combination of physical maybe etch, chemical etch. Okay. And then you put gate metal everywhere. So, this gate metal you see is coming everywhere, correct, it is coming everywhere. Now, there is photoresist right below the gate metal here and here. Now, if you do lift off, which means you dip it in acetone for instance or some kind of such solution, then this entire photoresist will go away, removing whatever is on the top, and resulting you get a gate which is sitting at a recess. This is a recess. Okay. It is a shallow etch in the channel, so that the gate below the gate the channel is thinner to have better control of the channel, and it also helps improve the breakdown, provided the gate leakage Ig should not be much. Okay. So, you should not etch so much that this becomes too thin. If this channel becomes too thin, then the gate will start leaking. Okay. The gate will start leaking, and if the gate starts leaking, then your breakdown will be poor. Okay. And so, that is not something you want. So, you want the gate leakage should not be very high. In that case, it will improve the breakdown. I will come to a slide later on as to how it improves breakdown, because the fact is that in the depletion region, which is here, you know, the depletion region here, all the electric field lines actually terminate at the gate edge. So, if this is your gate metal, all the electric field lines terminate at the gate metal, and you can show with mathematical derivation, which we are not going to do, however, that if you have a recess, you do the you find out the field profile, how the electric field is terminating at the gate, you will see that there is an improvement in the breakdown voltage. Okay, you will see that there is an improvement in the breakdown voltage. You essentially modify or tailor the electric field profile in the gate drain access region. In this gate drain access region, a recess allows you to modify the electric field profile in this region. Okay. In other words, the way the field lines terminate at the gate metal edge, this is the drain. So this edge is called the drain edge of the gate metal, actually the drain edge of the gate metal, and the way the field lines terminate at the gate edge of the drain metal, you have an improvement in your breakdown voltage. Actually this is mathematically derivable as to how the breakdown voltage will improve when you have a gate recess. Okay. It also helps you better channel control that I already talked to you about. So recess is an important process, and this is inherently done in most or almost MESFETs. Okay. This is we are talking about MESFET. There are of course different types of recess. Now these are 4 different kinds of recess architectures, gate recess. In one case you just etch the layer and then you put the gate there with some kind of a tapered profile. In another case you have a negative slope here, you have an inverted taper here, you put the gate. So every structure will have its own advantage and disadvantage, and again this is an N plus region, for instance. Maybe you have better contact resistance. Again the gate is sitting here, source and drain are here. You see here the source and drain are far away, right? Here the source and drain are little closer, the pads. Okay. And so you can see, and this is a more like a smooth edge profile, not an undercut, not an overcut. Again the metal can come here also as an overhang or whatever, but there are advantages and disadvantages to all of this. We shall come to that gradually. You have to remember that recess can help improve the breakdown only when the gate leakage is not so much, and the fact is that the breakdown is not the only parameter. You have to look at cutoff frequencies also, and for that you have to look at the capacitances, different capacitances in the devices, and this kind of a recess can actually influence these capacitances that are there in the device. Okay. So I will come to the definition of a gate metal and what kind of gate metals are used in subsequent slides, but I think we got an idea of, or a gist of, why self-aligned process is used, why recess is necessary, and how fabrication is typically done. I did not go through the details of each unit process because that needs a knowledge of microfabrication, microelectronic fabrication, lithography. There are so many steps such as metallization, metal evaporation, metal sputtering, plasma enhanced chemical vapor deposition of the dielectric, lift off process, lithography, spin coating, baking, etc. So you are encouraged to take a course on microelectronic fabrication if you want to understand those things, but we borrow those techniques and tools to fabricate a gallium arsenide MESFET. Okay. This is under the assumption that you know what a lithography is, what metallization is, etc., etc. Okay. And one of the things that I had in my slide which I did not explain is, for instance, for a gate metal, if you use a refractory metal, so you will use a titanium, tungsten, or silicide or something, and if it is not a gate priority process, which means it is an ohmic priority process, in that case you can use a non-refractory metal such as a titanium, platinum, gold. So titanium will come below, just on gallium arsenide, on top of that will come platinum, on top of them will come gold. Do you know why this particular stack or this kind of stacks are adopted? This is because titanium helps in adhesion. When you put the first layer as titanium, it helps stick to the gallium arsenide surface really well. Now basic semiconductor physics tells us that the metal work function matters when you are putting down the gate metal. For a Schottky contact you need a so and so work function, etc. However, in gallium arsenide or aluminum gallium arsenide surfaces there is something called Fermi pinning, which means there are defect states and donor like states on the surface which will pin the Fermi level, or in other words your Fermi level position will be fixed at certain value in the band gap, and your gate metal work function, whether you are using a low work function or a high work function metal, does not matter. Your Fermi pinning dictated by the traps and defects is what that matters. So if you have a band gap of say gallium arsenide which is EC and EV here, at the surface the Fermi level could be pinned say 0.7 electron volt from the conduction band. So the Fermi level will be pinned at 0.7 volt electron volt from the conduction band, for example. Does not matter what metals you deposit or evaporate, your Fermi level will be pinned to that level, which means you are free to choose any metal and you will get the same Schottky barrier height, which is 0.7 electron volt. So that is why then we use titanium, which has a low work function but does not matter, but it has a better adhesion process, so it gives you good adhesion. Now titanium oxidizes very fast, so you do not want only titanium, because the top layer will be oxidized to titanium oxide. So you need something like gold, which is non-oxidizing, which is a inert kind of a metal, and gold helps also in probing. When you put down the probe tips, when you want to wire bond the pad, gold is a very good metal, so gold is there, and platinum helps you prevent diffusion of gold below to the gallium arsenide layers, otherwise that will be a reliability problem. So you prevent gold, because gold can diffuse very fast, so you want to prevent the gold from diffusing inward, so you put platinum as a barrier. So the platinum has a barrier, is like a barrier, so titanium is a barrier, platinum, and then gold. Okay, so this is for a non-refractory. Even for a refractory you will use tungsten, maybe a gold process later on, and so on and so forth. Okay, so with that I think we are at the end of this lecture today, lecture 17. So in this lecture we went through the basics of the fabrication and also about self-aligned process. We talked about gate recess. Going ahead we will talk about in little bit more details about the process in terms of, say, the gate geometry, what kind of a gate is needed, a mushroom gate is needed. Okay, we will also talk about what kind of device parameters are desired for a low noise application or for a maybe a power amplifier application. Okay, so with that we will conclude lecture 17 here today. Thank you for your attention and time, and we will meet you in the next lecture. Thank you.